In their quest to appreciate the first stars and galaxies that illuminated the universe, stargazers often grapple with feelings of vulnerability. Yet, with every revelation, they move closer to enlightenment. This profound truth emerges from the remarkable discoveries of the James Webb Space Telescope, JWST, a $10 billion time machine marking its inaugural year of observations. Designed to reveal the faint infrared glow of the universe's earliest luminous objects, JWST has exceeded expectations. Its vision extends back to just a few 100 million years after the Big Bang, providing unparalleled data on infant galaxies, far surpassing any previous mission. The wealth of images of these cosmic infants has outstripped even the most optimistic forecasts. Many competing galaxies have appeared, astonishing scientists like Charlotte Mason, an astrophysicist at the University of Copenhagen. The unexpected proliferation of these early galaxies has sparked intense examination and debate among researchers and observers alike. Could these bizarre, massive, and bright early galaxies simply be artifacts, perhaps the result of flaws in the telescope's initial observations? Or if they are genuine, can they fit within established cosmological models? Alternatively, do they suggest a universe far stranger and more intricate than previously imagined, potentially challenging the foundations of the Big Bang theory itself? Join us today as we explore how the James Webb Space Telescope has transformed our understanding of the universe. But first, let's rewind to the universe's inception following the Big Bang. In the aftermath, as the universe cooled, electrons, protons, and neutrons combined to form mostly neutral hydrogen atoms, marking a period known as the Cosmic Dark Ages. Then, a critical event unfolded. Much of the universe's mass, composed of mysterious dark matter, began to exert its influence, ultimately leading to the formation of the first stars. These celestial beacons illuminated the universe during the epoch of reionization, triggering a cascade of events that shaped galaxy formation within a vast cosmic web. Meanwhile, Edwin Hubble's groundbreaking discoveries in the 1920s revealed that the universe is expanding. Subsequent observations, including those from the Hubble Space Telescope, uncovered an even more astonishing truth. The universe's expansion is accelerating, driven by mysterious dark energy, represented by the Greek letter lambda. By incorporating the properties of cold dark matter, normal matter, and radiation into Einstein's general theory of relativity, scientists have constructed the lambda cold dark matter model, which astonishingly aligns with a wealth of observational data. One way to validate this framework is by examining extremely distant galaxies, effectively looking back to the initial few 100 million years after the Big Bang, a time when the universe was simpler and easier for astronomers to analyze against theoretical predictions. The quest to image the universe's early structures began with the Hubble telescope in 1995. Over a span of 10 days, Hubble captured 342 exposures of what seemed like a blank patch of sky in the Hubble Deep Field. To the astonishment of astronomers, this seemingly dark area revealed thousands of galaxies at varying distances and stages of evolution, extending further back in time than expected. In 2016, astronomers made a remarkable discovery with Hubble, the most distant known galaxy at that time, named GNZ11, which appeared as a faint smudge dating back to approximately 400 million years after the Big Bang. This finding challenged conventional ideas about early galaxy formation, yet it did not entirely undermine the lambda model, partly due to its modest size, containing only 1% of the Milky Way's mass. However, astronomers required a more powerful tool to determine whether GNZ11 was an anomaly or part of a broader group of enigmatic early galaxies. Enter the James Webb Space Telescope, renowned as the largest and most powerful observatory ever launched from Earth. Situated 1.5 million kilometers away from any terrestrial interference and cooled to near absolute zero, JWST features a large segmented mirror and extremely sensitive instruments designed to unveil unprecedented details of cosmic dawn. JWST's initial discoveries have already exceeded expectations, providing glimpses of galaxies incredibly close to the onset of recorded history and analyzing exoplanet atmospheres with remarkable precision. As JWST's gaze reaches back to the universe's earliest epochs, it promises to yield invaluable insights into infant galaxies, potentially reshaping our understanding of cosmic evolution. The implications of JWST's early findings are significant, as they could fundamentally alter the foundational chapters of cosmic history and illuminate essential questions about our existence within the universe. As Mark McCaffrey, a senior consultant for space and exploration at the European Space Agency, aptly noted, these instruments are designed not to confirm the status quo but to challenge it, paving the way for groundbreaking revelations. A crucial method employed by researchers to determine the distances of celestial objects involves a variant of the Doppler effect, similar to locating an emergency vehicle based on the pitch of its siren. Cosmologists measure the redshift of galaxies, where the degree of redshift indicates the object's distance from us. JWST's data has already led to intriguing discoveries, such as the detection of galaxies with redshift values ranging from 11 to 20, suggesting a potential re-evaluation of early galaxy formation within the Lambda model. In summary, JWST's extraordinary capabilities have begun to unravel the mysteries of the early universe, challenging existing models and paving the way for a deeper understanding of cosmic evolution. Researchers delved into computer simulations of galaxies governed by the Lambda model, leading to a surprising finding. The early bright galaxies observed by JWST were significantly more massive than those simulated to form concurrently. This discrepancy has ignited discussions among established scientists and garnered media attention, with some asserting that JWST is testing the foundations of cosmology. However, not all researchers are swayed by these claims. One inherent challenge lies in the ambiguity of the Lambda model's predictions. While concepts like dark matter and dark energy are somewhat straightforward, visible matter exhibits complex interactions and behaviors, especially during the tumultuous early years following the Big Bang. These chaotic times must be approximated in computational simulations, introducing uncertainties into the models. Another complication arises from the difficulty in accurately determining the distances of galaxies shortly after the Big Bang. The ages of some purportedly high redshift galaxies have been revised due to updated telescope alignments. For instance, galaxy SPT 0615 JD was discovered within a cluster of galaxies whose light dates that there may be a closer object exhibiting the characteristics of a high redshift universe, attributed to factors like residual obscuration. This scenario features the anticipated emergence of new types of systems, complicating the analysis. The observations of these systems suggest that the galaxy labeled 749, regardless of its distance, presents a unique case that challenges conventional assumptions due to its low mass yet substantial dust content. To obtain more accurate distance estimates, researchers plan to utilize the James Webb Space Telescope's JWST advanced spectroscopy capabilities. Unlike photometry, which measures brightness, spectroscopy analyzes the frequencies of light, similar to conducting a DNA test to uncover family lineage. Initial observations relied on photometric data, but the integration of spectroscopy with photometry for 4 worlds has revealed redshifts up to 13.2, indicating light emitted 13.2 billion years ago. The release of these spectra has generated excitement among scientists, suggesting a potential shift in our understanding of the early universe. Brant Robertson from the University of California, Santa Cruz, posits that these findings imply rapid evolution in the early universe, with galaxies developing significantly faster than they do today, akin to a hummingbird's accelerated heartbeat compared to larger animals. However, questions arise regarding the compatibility of these rapid changes with the Lambda model of cosmology. While the JWST images captivated both astronomers and the public, scientists continued working diligently behind the scenes to understand the true nature of the observed galaxies and refine the parameters of cosmological conditions. A critical parameter in this context is the mass of early galaxies, essential for assessing their evolution over time and reconciling with Lambda expectations. Determining a galaxy's mass based on its brightness relies on assumptions about stars and galaxies, but Megan Donahue, an astrophysicist at Michigan State University, cautions that this relationship is, at best, an educated guess. It hinges on assumptions regarding the initial mass function, which dictates the statistical range of masses in which stars typically form. This initial mass function is crucial because, while hot, massive blue stars emit more light, the majority of a galaxy's mass is found in smaller, cooler red stars. If the initial mass function varied in the early universe, the galaxies observed by JWST could appear brighter than they actually are, potentially complicating our understanding of galaxy evolution. Rachel Somerville, an astrophysicist at the Flatiron Institute, suggests that adjustments to the initial mass function and other factors could align the ancient galaxies seen by JWST with the lambda model. She proposes that gas in the early universe cooled and condensed more rapidly, leading to quicker star formation. Another intriguing possibility is the role of black holes in the early universe. Supermassive black holes observed at redshifts of 6 or 5 billion years post-Big Bang might explain the brightness of early galaxies, even if they are not exceptionally large. Evidence that the lambda model can accommodate some of JWST's early universe findings comes from simulations conducted by Benjamin Keller and his team at the University of Memphis. Their results, available on the preprint server arcs4.org, demonstrate that the simulated galaxies align with JWST observations, alleviating concerns about the compatibility of the observed galaxies with the prevailing cosmological model. Additionally, JWST's findings hint at the existence of population 3 stars, the first generation of stars that ignited, untainted by metals from previous celestial ages. These stars may have played a role in the reionization of the universe. The discovery of exceptionally large and ancient galaxies in the early universe, as observed by the James Webb Space Telescope, initially unsettled cosmologists, challenging the established cosmological model. However, recent insights suggest that the model can indeed accommodate JWST's discoveries. Virtual simulations based on the Standard Model indicate that the universe could plausibly produce galaxies similar to those observed by JWST. While initial data seemed at odds with cosmological models, astronomers now speculate that gaps in our understanding of galaxy formation may be the underlying cause. Potential explanations for these surprising discoveries abound. Some suggest that early stars formed more readily than previously thought, while others propose that abundant dust in these galaxies could distort their appearance, making stars seem older. The role of black holes, particularly their influence on enhancing cosmic brightness, also warrants investigation. Despite these potential explanations, the vast size and age of the observed galaxies remain perplexing. Further observations, especially those employing spectroscopy to analyze starlight in greater detail, are crucial for confirming the nature of these galaxies as astronomers delve deeper into these mysteries. Anticipation builds for the forthcoming spectroscopic data expected this spring, as this undertaking represents a journey of exploration and discovery, pushing the boundaries of our understanding of the universe's infancy. A significant portion of JWST's observing time in both Cycle 1 and Cycle 2 is dedicated to probing the earliest known galaxies in the universe and searching for exoplanets. For instance, Daniel Eisenstein of Harvard University plans to leverage the telescope's capabilities to pursue galaxies formed just 200 million years after the Big Bang, beyond redshift 15, an achievement never before realized. Meanwhile, Rohan Natu from the Massachusetts Institute of Technology leads a project using gravitational lensing from a galaxy cluster to amplify the brightness of smaller objects, potentially revealing clusters of population 3 stars, the first generation of stars in the universe. In Cycle 2, focus on the TRAPPIST-1 system, a group of 7 Earth-sized planets orbiting a red dwarf star, continues. While 3 projects were selected in Cycle 1, only one has been approved this time, led by Michael Gillen from the University of Leuven in Belgium. Gillen aims to investigate the atmospheres of TRAPPIST-1b and TRAPPIST-1c, the 2 innermost planets in the TRAPPIST-1 system. Previous studies suggested that TRAPPIST-1b might lack an atmosphere. However, Gillen intends to employ a method of measuring temperature differences between the planet's sunlit and dark sides to confirm this and explore implications for potentially habitable environments. Christopher Glenn from the Southwest Research Institute in Texas plans to utilize JWST to study Saturn's moon Enceladus, which may harbor a subsurface ocean beneath its icy exterior. Glenn hopes to find evidence of oceanic chemistry on Enceladus' surface, including compounds like ammonia and organic molecules, which could offer insights into the moon's habitability. Nancy Levinson of the Space Telescope Science Institute acknowledges the inevitable disappointments from unselected projects, but encourages researchers to seize future opportunities in later cycles. With the deadline for Cycle 3 proposals approaching, there remains hope for scientists to pursue vital research objectives using the JWST.